Hi folks, welcome back to 5.3, the fundamental theorem of calculus. We are in video number 3 for this section, and we're going to keep going with that fundamental theorem of calculus part 1, okay? So just as a refresher, the fundamental theorem of calculus part 1 basically says that if you take the derivative of the antiderivative, you should end up with your original function, okay? Let me say that one more time. If you take the derivative of the antiderivative, it gives you your original function. All right, so we've done a few examples where we looked at sort of different bounds and how that impacted us, and we did these all the long way. And you are welcome to do them the long way, but I feel like many of us out there really appreciate when we can find a shortcut way to handle the same question. So here's what we're going to do. We're going to take a look at example 5 and example 6 using a shortcut method. So here, if we look at example 5, okay, it looks like we have a constant at the top, all right, and our variable is on the bottom. So because the constant's on the top, that's like all the case B's that I saw for example 3 and 4. And so for part 4b, I noticed that I had the constant in the front, so then I had the negative sign in my answer. And for 3b, I had the constant in the front, so I had the negative sign in my answer. And that's always going to be true when I have the top bound as the constant and the bottom bound as x. So we can say that this equals negative, and then just put in our bottom bound. There shouldn't be a sign there, sorry. Negative 3x sine x. And that's it, okay? Now you do have to know it's negative because the bound is on the bottom. And if I switched it, if I said d dx of 5 to x of 3t sine t dt, I would get just regular 3x sine x, okay? So where the constants are and where the variables are impact the sign of your answer. Okay, let's take a look at example 5. So I've got d dx, that's good, of an integral, that's good. So derivative of an antiderivative will give me the original function. My bottom bound is the constant this time. So that's kind of like this little example we did right here. What's different though is that our top bound isn't just x, it's a function of x. And so what we're going to need to do is use chain rule. So we're going to plug in 3x squared everywhere we see a t. So that will give me 1 over 2 plus e to the not t, but 3x squared. That's the first step. Then you multiply it by the derivative of 3x squared, which is 6x. And when you clean that up, you'll get 6x over 2 plus e to the 3x squared. And that is how we use the shortcut, okay? So where the bounds, or what the bounds are, whether they're in the top or the bottom, definitely impact your answer. And that good old chain rule, it doesn't go away, it keeps coming back. Anytime it's not just x, you have to use chain rule, okay? So let's take a look at 2 more examples before we move on to the fundamental theorem of calculus part 2. So example 7. Let capital F of x equal the integral from 1 to square root of x sine t dt. And they want you to find the derivative. So here they're asking us the same question but in a slightly different way, because they're saying find d dx of this antiderivative. And so we know derivative of the antiderivative should give us our original function. It's just a slightly different way of asking that same question. So let's use our shortcuts. Where is our constant in the bound? Well, it's on the bottom, so I'm not going to have to change the sign of my answer. But the upper bound is more like example 6, where because it's not just x, I'm going to need chain rule. Okay? And I'm going to go ahead and write square root of x as x to the 1/2, just so I know those are the same. That's going to help me when I need my chain rule part. The first part, though, is pretty straightforward. Everywhere I see a t, I'm just going to put square root of x. So sine square root of x. Now comes the chain rule part. Times derivative of x to the 1/2 is 1/2 x to the negative 1/2. Let me clean this up some more. Sine square root of x equals 1, oh, not equals, sorry. Times 1/2, 1 over 2 root x. And let's clean this up even more. Sine root x over 2 root x. If you think that it's okay to cancel that and that is not okay. That's why they're in red, okay? Do not cancel those square roots of x. Why can't you cancel them? Because the square root of x on the top is being signed. Like, this is together. You can't separate them, okay? This on the bottom says 2 times square root of x, so that's different, okay? So our answer is just square root of x, or sine of square root of x over 2 root x. All right, let's take a look at one last example here. I take a look at this. I realize my top bound has a function of x, whereas my bottom bound has x. So kind of a mix of the other examples we've seen. Okay, and same thing, they're asking us for the derivative. So d dx of the integral of x to 2x of t cubed dt equals, all right, well, I'm going to start by saying everywhere I see the t, I'm going to put the top bound. And then everywhere I see the t, I'm going to put the bottom bound, and I'm going to subtract them. So t cubed would be 2 to the x cubed times derivative of 2x is 2 minus x cubed. And I don't have to use chain rule here because it's only x. And when we clean that up, we'll get 8x cubed times 2 minus x cubed, or 16x cubed minus x cubed, or 15x cubed as my original function. Okay? So hopefully these other examples help clarify that fundamental theorem of calculus part 1, which again really just means if you take the derivative of the antiderivative, you end up with the original function. Okay. Let's move on to the fundamental theorem of calculus part 2. So the fundamental theorem of calculus part 2 says that if f is continuous over a given interval, and f of x is the antiderivative of f of x, then, and we've seen this before, if you have a lower bound and an upper bound, you're going to take the antiderivative and you're going to plug in the top bound first, and then you're going to subtract the bottom bound. So this fundamental theorem of calculus part 2 is really saying the same thing as when we learned about definite integrals back in 5.2. All right? So definite integrals comes from the fundamental theorem of calculus part 2. So let's take a look at an example. So example 9 says evaluate from negative 2 to 2 the integral of t squared minus 4 dt. So remember, when we say the integral, what we're saying is this. I want you to find the area between curve and the x-axis. All right, so find the area between the curve and the x-axis from x equals -2 to x equals 2. All right, that's what those symbols are saying. They want you to find the area between the curve and the x-axis from x equals -2 to x equals 2. And in this case, I suppose I should have used t to be a little bit more accurate, from t equals -2 to t equals 2. And so we have a graph here. So t squared minus 4 looks like a parabola. And those of you who had me for pre-calc know that this -4 means you move that parabola down 4. And so we end up with a parabola whose vertex is at -4. And the area that they're asking us to find is the area in the blue, okay? And it's in the blue because that's where the x-axis is, so it's between the curve and the x-axis, all right? So we're going to do this problem by using our idea of definite integrals, or this fundamental theorem of calculus part 2. So let's go ahead and set up our integral. So the integral from -2 to 2 of t squared minus 4 dt. And that's going to equal, let's see, where did t squared come from? Well, it's t cubed, and the reciprocal of 3 is 1/3. Minus 4 came from 4t. No plus c because I have bounds. So draw the bar, put a 2 at the top, and a -2 at the bottom. All right. So now I'm going to go ahead and plug in my bounds. So I have 1/3 2 cubed minus 4 times 2. All of this comes from our top bound of 2. Okay, so this here is your f of b, or your antiderivative with b plugged in, minus 1/3 times -2 cubed minus 4 times -2. And that comes from our lower bound plugged in. So that gives you the minus f of a. Okay? Now, I cannot emphasize enough how important it is that you double check your signs. Okay? I have seen students set up all the calculus right and get the answer wrong because they didn't get their signs right. Make sure you double check your signs. And here's why. So in the first part, the f of b, I end up with 8/3 minus 8. In the green part, I end up with -8/3 because -2 cubed is -8, and then plus 8. All right, so if you don't distribute this sign right here, you're going to get that sign wrong. And now we have to take this minus sign and distribute it to that. So I've got 8/3 minus 8 plus 8/3 minus 8. Okay? Now we're going to combine, so 16/3 minus 16 equals 16/3 minus 48/3, and that gives us a final answer of -32/3. Okay? Now, we're going to stop here, but when we come back for the next part of the video, I'll show you what happens if you made a sign mistake and how you can use your diagram to tell you that you were wrong. Okay, so our answer is -32/3, which makes sense because our area here is negative, and that's okay. All right, folks, I'll see you back here for the next part in our section of 5.3. See you there.